The only thing it doesn't do is it doesn't seem a periodic table. I haven't quite mastered that one. Been two cameras. Okay. We got sort of an introduction to the basics last time. And here. Now we're going to look specifically at measurements. How do we do measurements? Or even why do we do measurements in science? Chemistry in particular. Whenever scientists go into the lab, actually go into a growth chamber or a greenhouse or out in the field or into a quarry or wherever they go, eventually, first of all, they'll make some types of observations. Some of them might just be kind of a general idea of what the phenomenon is. Does it have color? Did it make a big bang? Things that affect the senses. But eventually, some measurements are going to have to be made. And that's what we call quantitative data. You have to quantify it. In other words, that means you need a number. You don't just need a number. You need a number and a unit together when you make a measurement. If I were to say, I'm 71, you might just automatically think, oh, I'm 71 years old. Not quite. I'm bumping up against it, but I'm not there yet. But I don't mean 71 years. I didn't say what it was, so, how are you to know? I mean 71 inches tall and 5'11". So the unit is as important as the number. And the units can be expressions of different things. It could express length or height, in my case, as I was saying 71. It could be, what's my mass? I'm not sure what it is in kilograms. It's like 200 pounds, so we could convert that. We'll talk about that later, how to do conversions. But these measurements, usually, the direct measurements that you make have something to do with mass or volume, length, time, temperature, pressure, concentration. There are others that can be made, of course. For instance, we could make measurements about helium on the sun. We just need a telescope and a spectrograph to take the light that we bring in and spread it out into its various colors. And you can also quantify those colors by what wavelength are they. We have a certain spread of wavelengths for that particular element. So those have numbers too. And for that, if it's a wavelength, then we use the Greek letter lambda for that. Wavelength, it might be something like, I don't know, 620 nanometers. Right? So nanometers doesn't mean anything to you right now, but that's the wavelength of the light. In science, we use the metric system. Every day in this country, we use the English system. Sometimes it's called the Imperial System because it originated with the kings. Right? They dictated the units of measure, like the size, how much is this coin, how long is a foot. I mean, it's the same as the king's foot. Right? But we still commonly use these types of measurements, and everybody has sort of an intuition about, when I say a gallon, you have a pretty good idea what a gallon is. Yeah. But other things are creeping in, like 2 liters of pop. We know what a 2-liter bottle looks like. Say, okay, I know what that is. If you ever look on a gallon jug of milk, you'll see next to the gallon, maybe in parentheses, it'll say 3.8 liters. Liter is another measurement of volume in the metric system. Okay? In science, this is the system, the metric system. And it's established by it's an international system, a consortium of agencies that have agreed upon standard values for each of these units, types of measurements. When I was doing research in agronomy, which is crops and soils, when I go out and talk to farmers, because we had experiments on their fields, cooperating with farmers, we put an experiment over in this corner. When I talk to the farmers, I talk to them in terms of bushels and pounds per acre or bushels per acre, that type of thing. That's an English system. But when I go to publish the work, I have to convert all that stuff into metric system because that's the scientific publication. Now, there were a few publications that bridged the gap, and they would put the units in both because they were being distributed to farmers. So they needed a type of measurement that the farmers understood. Now, with the younger farmers coming along, I mean, they're trained in metric systems, so eventually it'll probably die out. They're also doing a lot of stuff with technology. I've seen Louisiana fields that were being leveled. You wouldn't think that you'd have uneven fields in Louisiana. But yeah, they go like this, and you can see once after big rain, you can see the low spots, the water puddles. You don't want that on your crops. So they set up this laser beacon, either at the edge of the field or in the center of the field, and it just spins around, this laser beam. And the tractor you're on, you're pulling a grader, and the grader has a laser detector on it, and it keeps adjusting that to maximize the energy from that laser that's spinning out there. So if you start to drop down like this, then it'll raise it up to meet the laser. But if it rises up above the laser, it'll bring it back down, and when it does that, it grades off some of the land. So you can get an extremely flat field, like hundreds of acres, just by using this equipment. And then, of course, when they're plowing the field or when they're harvesting, each tractor has a GPS on it, so it knows exactly where the tractor is. I mean, you could just set it, pre-program a path that the tractor's going to take, get up in the cab and turn it on, sit back and eat a sandwich and, watch YouTube on your phone or something, and it'll just go ahead and do the whole process for you. Now, we're talking about lots of money, but, it's out there. But the metric system, yeah, go ahead, sign in. The metric system is more convenient to use because it's decimal based. You know what that means? So if you have this position here, 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 this might be the ones position, this might be the tens, the hundreds, the thousands position. So all you have to get a bigger number as you go left. Like we could have 2, 3, 5,132. Everybody understands that. In fact, even the English system has some of that built into it. But the metric system, the units of measure, they're all based upon metric and varying sizes of multiples of 10. It's a decimal system. And that's a whole lot easier to deal with than these odd units, like 12 inches in a foot and 5,280 feet in a mile. Quarts, 4 quarts in a gallon, 2 pints in a quart. What is 2 cups in a pint? I don't know. Below.
I want to say 4.
Yeah, I think it's 2, 2, and 4 get up to a gallon.
I use the metric system.
Ounces, you know, a pint's a pound, so that means it's 8 ounces, 16 ounces, and 8 ounces in a cup. You know, and then there are liquid ounces and there are solid ounces. So it could really be a mess. In fact, England, I don't know when they did it, but now they kept the pound, but they did away with all those odd divisions. Now a pound is 100 pence. That's it. So they went to decimal. And midnight tonight, they're out of the European Union. You know that? This is it. Brexit is going to happen tonight at midnight. They're no longer, not England, but Great Britain is no longer under the thumb of the bureaucrats in Brussels. Took them long enough to get there. Anyway, but they do. Everywhere else in the world, they all use metric system. And even your cars now, your speedometer, it has miles per hour, and it also has kilometers per hour on. Okay. Okay, so metric system is what we use for scientific work. And but the units that we choose for the various measurements may be the wrong size. Like if you have you're measuring things in meters, but you're trying to measure a bacterium. You know, how big is a bacterium in meters? Well, we need prefixes that modify the base unit. So if the base unit is meters and we're measuring a bacterium, we'll want to measure it in maybe micrometers. So these prefixes have a meaning. They're constant values. This one is 10 to the minus 6 times whatever. Okay, so the unit, the micrometer unit, you would have to multiply it times 1,000,000 to equal 1 meter, right? Because it's so small. But each of these prefixes has a value that has to be multiplied by the base unit. Okay, so let's look at some these multipliers. Here's a good one to remember. K, little k, or kilo, means 1,000 times the base unit. So a kilometer, or kilometer, is 1,000 times a meter. And if you're going 100 kilometers per hour, you're going 100,000 meters per hour. Okay. Deci means a tenth. This little d means a tenth. Centi means 100. Like centimeters. Like a meter stick will have 100 divisions on it, and each one of those will be a centimeter. A millimeter would be 1,000 divisions of that meter stick. Right? Because milli means 1,000th of. 1,000th of a meter, millimeter. So it takes 1,000 of them to make a meter. And then we did the micro. This letter is the Greek mu, which is a small letter for mu. And that's 10 to the minus 6. Nano, you've heard of nanotechnology, when they make these very small particles, and they embed them in your clothes. They do a bunch of other stuff with them. But they're on the order of a billionth of a meter in length. And so we're getting down pretty small. You need a microscope to see those. And then picometers, you won't encounter those probably anywhere in everyday conversation. Only if you start talking about unit cells in crystal structure of an element. Then you'll speak in terms of picometers, or the distances within atoms. Okay, so we went, this one's pretty large, and then we went down smaller and smaller. Everybody knows what mega means, right? Megabytes in memory size of a computer is 1,000,000 bytes. Right? And gigabytes is 1,000,000,000 times. Now we're up to terabytes, 10 to the 12th bytes of memory. That's becoming affordable. I mean, even solid state is becoming more affordable at that size. But these are all prefixes that modify the size of the base unit. And it doesn't matter what the base unit is, these are always those multipliers of the base unit. Okay? So if the meter is the base unit of length, it's also the fundamental unit. So what's the difference between a base and a fundamental? A base unit you can define whatever you want. I mean, if you want to use meter as your base unit, well, actually, meter is the base unit but it's also the fundamental unit. And what the fundamental means is that is the standard of length. Right? It's not just the base unit, it's also the standard. And originally, the meter was a fraction of the distance between the equator and the North Pole on the meridian that passed through near London. So once they established what that was, then they created several platinum iridium alloy bars that were that length. And they created these oblong bell jars and put them in there. They were actually double bell jars filled with an inert gas so that they would not corrode. And they stabilized the temperature. They stuck them in a cave in France somewhere. And that was your standard. So if any scientist needed to standardize a meter for other type purposes, they would have to go to that cave and compare it, or go to the facility attached to the cave and compare the lengths and see, I think this is a meter, but what is it actually compared to your meter? Because yours is the standard. Okay? Well, now we've simplified it. So now, if you have the proper equipment, you can take your laser-based machine, and it will count the number of wavelengths of a certain laser light of a certain color, and that establishes the meter very accurately. In fact, probably more accurately than the rod. Okay. Yep. Question? No? The base unit for mass is the gram. Okay, so the gram is pretty small. And it's sort of a holdover. It's a historical oddity that we just had to keep because everybody was using it. So the gram is the base unit. But the fundamental unit, the one that establishes the standard, is the kilogram, 1,000 grams. Now, why would that be? Well, if the gram is like this, then what if you miss that weight, or mass? If you miss the mass by that much error, that could be 1, 2, 3, 4% error, and that's unacceptable. So they said, okay, we need 1,000 of those. So they created a mass that was 1,000 or 1 kilogram as the standard, so that if you were off by the same amount here, the percentage error would be much, much lower, an acceptable amount. So that's why the gram is the base unit that the prefixes are multiplied by, and the kilogram is the fundamental unit that establishes the size of that mass. And there's also a fundamental difference between mass and weight. We use the terms interchangeably. I still do. In fact, you may see a method where you're supposed to acquire a certain amount of a powder or a solid. So you go to the electronic balance and you divvy out some of it until you get to a certain mass. I still say weigh. Weigh this to 0.001 gram accuracy. But what we mean is mass. The difference is that mass never changes. If you have a certain mass of something, it's the same no matter where you are in the universe. Right? So 10 kilograms on the surface of the Earth is 10 kilograms on the surface of the moon. Right? But 60 pounds, which is the measure of force or weight, 60 pounds on the Earth is only 10 pounds on the moon. Okay. So the difference is between the two is that mass establishes how much substance you have right there. And weight establishes what's the effect of gravitational field on that substance. So the Earth has a stronger gravitational field than the moon, so it's going to have a different weight. Okay, the liter is the base unit of volume. Right. So we get, actually, you can buy pop-in liter bottles too. Are these bottles are half liters, are they? Maybe not. They're in ounces, aren't they? What is that, 20 ounces? Or 16 ounces? 16 ounces, and then in parentheses it'll tell you how many milliliters. Right. So what we've done is we've taken the base unit of liters and modify it by the prefix m, little m, for milli. So the size of the milliliter is 1,000th of the size of the liter. So if you have a liter volume here, then the milliliter will only be like that. We modify the base unit and the fundamental unit for that matter. And the volume is also established by convention as the liter. Okay. I think, well, it used to be, not anymore. The operating, not the base unit, but the operating unit in the medical profession was cc, cubic centimeter. And I don't know, hospitals may have some product that's hold over from years ago that still has cc written on the side of it. But now they'll write ml, little m, big L. For milliliters, there's no difference. They're both the same exact size. The cc, cubic centimeter, and the milliliter are exactly the same size. So if you see something that says cc on it, just think milliliters, it's the same thing. So relatively speaking, we have this cube that we know is 1,000 cubic centimeters. So how do we know it's 1,000 cubic centimeters? And this is 1 liter, is each side is 10 centimeters. 10 centimeters that way, 10 centimeters that way, 10 centimeters this way. So 10 times 10 times 10 is 1,000. So 1,000 cubic centimeters is 1 liter. That's established by convention. That's 1 liter. And that just points out what I just told you. They're equal. Okay. Well, let's see. What do we need to know? A meter is a little bit longer than a yard. Why? Because it takes more than 1 yard to make 1 meter. Right? If it takes more than the unit to be equal to 1 of the other unit, that means this is the smaller unit, doesn't it? It has to be. And if you look at a meter stick, how long is a meter stick? It's not 36 inches, right? That's a yardstick. Meter stick stretches it out about 3.5 inches more. Okay, it's 39.36 inches for the meter. I've got a couple of meter sticks in my van I keep with me all the time. Mass. Okay, so if 1 gram is equal to the fraction 1 divided by 454 pounds, which is the smaller measure? Well, this is a fraction of a pound. So the pound has to be the bigger one than the gram. And you could also say it this way, right? If we say 1 gram equals 1 over 454 pounds, then algebra says we can take that 454 and put it over here, right? Divide on this side, multiply on the other side. So you can say 454 grams equals 1 pound. Okay. And we have an idea of what a liter is. I'm not going to labor that point. So which of the following represents the largest measurement of mass? The largest unit of measure for mass? Okay, they all have the same base unit, right? Gram, 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 gram. So you need to look at the prefix, right? So this prefix is non-existent. It's just gram, right? So is this one smaller than a gram or larger than a gram? Oh, right, microgram. How about nanogram? That's even smaller than a micro, isn't it? Kilo. That's the biggest one, isn't it? Because it's 1,000 times. Okay. Now we're going to talk about uncertainty. In any type of measurement, there is uncertainty. You just have to accept it. There are various reasons for uncertainty. Some of them are obvious, some of them are not so obvious. One obvious one might be that I'm slightly colorblind, right? So I might report something as blue when it's really green. You know, I don't go when the light turns green. I go when it turns blue-green. Color blindness is more common in men anyway. But every type of measurement you make is going to be uncertain to a greater or lesser degree. So what you try to do is make it as certain as possible. Minimize the uncertainty. But we have to know and agree upon what we mean by uncertainty. Okay, so the authors of this book start off with a discussion of exact numbers. Now this is agreed upon, and we're saying that an exact number is one whose value has no uncertainty. Now we know that's not true, but for some applications we have to accept some numbers as certain. The whole number, every part of it. And usually what we're talking about is either things that you count, right? So if you want to call it a pretzel or a pencil or a marble or whatever the object is, you can say how many of them there are, but you can't say what a fraction is. Or it's like, it used to be that the average number of children for the American family was like 2.4. So who's got a 0.4 of a child, right? So you have to agree upon an exact number. And in that case, for each individual family, you'd have to count. Like you might have 4 children, you might have 2 children, you might have 1, so forth. Used to be a whole lot more. I think my dad came from a family that had 10. It was more common years ago to have more children. Or simple fractions are considered exact numbers. And then there's one other type that we just have to agree upon. And those are conversion factors, where you have, by definition, so many objects equal to, or so many of this equal to so many of that. It's an equivalence. So we would say 12 objects equals 1 dozen. That establishes an exact ratio, right? So these can be made into conversion factors, and I'll talk about conversion factors in just a minute in more detail. But this establishes exact numbers. So that means there are inexact numbers. Now we have to agree upon what do we mean by an inexact number. Well, even with inexact numbers, some part of the number, it can be considered certain. There's no variability in the digit, like we have a number with 4 digits. Some of those are certain. We know exactly their value. But by convention, if you write that number like that, these are certain. And this one is uncertain. So what do we mean by uncertain? It's a guess. It's just a guess. But since any scientist that looks at your data, looks at a number that you produce, they automatically assume that you have given them that number with certain values, and the very last one is uncertain. If you write the number like this, let's see. Now you're saying that this one is certain and that one's uncertain. That's by convention. The last one is always the uncertain one. And that establishes the inexactness of the number, the last uncertain one. Okay, which one of these is true? An exact number is a number that has no uncertainty associated with it. Yeah, that's true. An inexact number is a number that has a degree of uncertainty associated with it. That's true too. Inexact numbers occur anytime a measurement is made. They're all true. Yeah. Okay. So I sort of jumped ahead. This is just what I was talking about with writing a number. Now, what does that mean in practical terms when you're actually making a measurement? Well, for example, if we're measuring the length of an object, if this object is the same length as that object, but we use a different measuring device, this one is divided off into centimeters. That's it. Right? The exact part of that number can be established by how close is it to one of these lines. Right? So the exact part, the certain part is 3, because it's between 3 and 4. The uncertain part is a guess because we don't have any numbers in there. I mean, no lines. Right? So we're not saying that we know where the millimeters are located. Right? It takes 10 millimeters to make a centimeter. So we guess, and we say we guess that between 3 and 4 there are tenths. We think it's about 7/10 of the way from 3 to 4. So we're saying that 3 is certain, 0.7 is the uncertain. Now, if we use a ruler that does have millimeters marked off, then we can say that 3.7, right here, 0.7, is a certain number. So now we go between 0.7 and 0.8 and estimate the distance there. And whoever built this slide says, I think it's 4/10 of the way between this line and this line, which means actually 4/100 in the measurement, right? So this one is certain, that one's certain, and now this one is our guess. Okay. So it depends on the device that you're using also as to which one you can guess and which one you can say is certain. Now, now that we've established that, we need a method, we need a way to know how to ascertain what numbers we can keep in a measurement, especially if we're going to multiply, divide, add, subtract different numbers, calculations. So that's what the significant, that must be the same one. You probably got out of the trash can. As long as he stays there, we're fine. Significant figures. So we're saying the significant figures are the ones that include the certain and that one uncertain digit. So in that number I showed you before, there were 4 significant digits, significant figures. We had the 3 certain and the 1 uncertain. And then when I added a decimal on the end, we actually had 5. We had 4 certain and 1 uncertain. Okay, so here are the rules. First, we have to decide what are the number of significant figures in a value before we can give you rules on how to multiply, divide, add, and subtract. So we've got to establish how many significant figures you have in each one of the numbers that are going to enter a calculation. Then you can say, what do you do with them? Right. So this one's the easy one, the first one. A number that is all non-zero digits, every one of them is significant. Right? We have 3 certain and 1 uncertain. So you have 4 significant digits in that number because they're all non-zero. So that begs the question, what if you have a 0 in there somewhere? The answer is, it depends on where the 0 is located. Right? So if the 0 is leading, like to the left of the non-zeros, and there are no non-zeros out here. See, these zeros are off by themselves to the left, and there are no non-zeros in there anywhere. Those 2 zeros are not significant. The only significant figures you have are these 2. 1 certain, 1 uncertain. Okay? So leading zeros don't count, ever. What if you have a 0 that's bracketed or confined by non-zero numbers? That one is significant. If it weren't, if we couldn't keep it, then we couldn't say where the uncertain one was. So this one, and this one are certain values. And this one's the uncertain. I see puzzled faces, but I don't see any heads twisting around, so that's good news. Okay, so that 0 is significant because it's confined by non-zeros. And it just so happens to have a decimal there. It doesn't matter whether it has a decimal or not. If it's got non-zeros on either side, that 0 is significant no matter where it is. Decimals are not. Then the only other possibility is zeros on the right-hand side. Right? So this one has another caveat built in. If there's a decimal point there, those zeros are significant. Right? If there's no decimal point, then those zeros are not significant. Now, there's a difference between explicit and understood decimals, right? If I write this number like that, right, without the decimal, where is the decimal that you assume to be? Right here. But when we're doing significant figures, there's no decimal there. Okay, see what I mean? And that means that these are the only two significant figures. One certain, one uncertain. Those zeros don't count if there's no decimal. So if you want those to count in a measurement, you put a decimal there. Or if it happens to be 9.300, you put the decimal where it's supposed to be. Right? But in this case, we assumed the decimal was there. So if we're going to make those two zeros significant, we have to put one there. An explicit decimal makes those two zeros significant. So now there are 4 significant figures in that number. This is the uncertain one. Okay? Okay, I jumped ahead a slide. That's what I just said about this number. Okay? All right, which types of zero in a number are considered significant? Well, let's see. Leading, no. Leading, no. We're using test-taking techniques, you know. If it's got to be both of them, all you have to do is find one wrong and then it doesn't count. I mean, that's false. False, false. Confined and trailing zeros, no, because that's a special case. Confined and trailing zeros with a decimal, yes. That's the one where the zeros are considered significant for any one of those answers. That's the only one that gives you all those conditions are correct.
I'm just thinking about how that they're significant on the right side with the decimal, but if they're all on the left side, even with the decimal, they're not considered. So I'm trying to figure out how they came about that rationale.
They're just placeholders. There's another way to think about it. Let's see. I don't want to jump too far ahead. I can jump a slide at a time, and it will mess you up too much. No, we're not ready to talk about scientific notation yet. But when we do, if you take those numbers and convert them to scientific notation, those zeros on the left disappear.
Oh, yeah, it goes
Okay.
like that.
Yeah. So that's one way to think about it.
It makes sense now.
Rounding. Okay. So your calculator or computer that does calculation for you spits out a number, and it has no idea what significant figures mean. Right? It's not built into its algorithms. It just gives you the most digits that your display will allow, right? Or that you select when you set it up. So we have to round numbers. When we get an answer, when we see a value, we have to round the number to the correct number of significant figures. And in this class, we're going to keep it really simple. It's like the one you learn in grade school. 5 or more, 5 or more, you round up. Less than 5, you round down. Now, that doesn't mean you round the 5 up or the 5 down. You round the 1 right to the left of it. So if we're going to keep 3 significant figures in this number, they're all non-zeros. So we count from the left, 1, 2, 3. That's the one we need to know. How is it rounded? So we look just to the right. Ignore everything else. Right? You don't round. You just look right to the right of that number. That's less than 5. So we throw these out and keep the 2. Okay? In this case, Those zeros are significant, right? Because they're bracketed by non-zeros. But we want to round to 3 significant figures in this one. So this one's 6, greater than 5. So that means this 0 has to be rounded up to a 1. So we round 5.01. Okay. Now, we've got 2 or more numbers that have to be multiplied together or divided. The same rules hold for either one. And the rule is, when you multiply these 2 numbers and your calculator spits out something with just like an infinite number of decimal places, you can write them all down. But then you've got to decide based on what you started with. What is the one with the least significant figures? Right? So you know this one is 4. That's a bracketed 0. And this one is 3. So your answer can only have 3 significant figures in it. Okay? So we got to pick 1, 2, 3. We've got to round this one based on what's to the right. And since that's less than 5, we throw those out and keep the 5. So rounding that calculation result is 15.5 for this. Okay? That's multiplication division. Right? You do the same thing if it was a divide. We divided this into that, we get something over here, and you just round it to 3 significant figures. Okay? Then, of course, there are the add-subtract rules, and they're different. The add-subtract rules require that you line up, well, we're saying line up the decimal place. If there's a decimal place, line up the decimals. I'll show you a weird case on the next slide. But if they're decimals, you line up the decimal places, then you just add them together like normal, right? So you get 10.733. Now, how many of these can you keep? Well, you look which one's the shortest one. This one. You have to round to the 10th place here. Okay? That's add-subtract rule. Now, try this one. 9,333, and you want to add 1,400, right? Okay. How many significant figures in this one? 4. How many in this one? 2. To the hundredths place, thousandths, hundredths place. So we have to stop at that position when we get our answer. So our answer would look like, we have to stop at the uncertain digit, the least certain. So that would be the one furthest to the left. So you can add them all up like that, but then you have to round it off to this position right here. Not to the number of significant figures, but to the position of the uncertain digit right there. So that would be rounded off since this is less than 5, it'd be rounded off to 10700. Okay? And that only has 3 significant figures in it. This one had 4, this one had 2, but the answer can have 3. And so add-subtract is a little harder to grasp, I think. Now, what do you do as a practical matter when you're making measurements in the lab and you need to combine values from 2 different measurements, and one of them is measured more accurately than the other? What's the limiting factor? The least accurate device determines the significant figures in your value. And you still use the rules. Right? You still use the add, subtract, multiply, divide rules. Just recognizing that the value you get from this one, because it has finer divisions, is overruled by the one that's less accurate. So if we look at this one, let's see, what would this one be? In this graduated cylinder, this is divided by what? This is 0.2.468. So this would be 2.80. right? Because there's a line for 8, and then the next one we estimate, and it looks like it's right on the line. So that one will be 2.80 milliliters. How about this one? This one is 0.2. Oh, 80. Okay. So if you're going to combine those volumes, you're limited by this one. Right? So that one's significant. Our answer is limited then. We add these together, and that will be 0.803. And since this one's 0, we round it off, and the answer should be this. Now, I hope the slide shows that. Or does it make me a liar? Yeah. So that would be the total volume. It's limited by the least accurate device. Okay. Exact numbers. So when you're doing a calculation of some type, exact numbers are those that have infinite significant figures. In other words, you don't have to consider them at all. When they enter a calculation, you can ignore them and just look at the numbers that are actual measurements, and not conversion factors. Okay? So if we use this number, and we were saying it's 2.5 centimeters per inch, we use that in a calculation, then the 2.54, it might as well be 2.54000000. It doesn't matter. All right. So if your calculator gives you this answer, when you multiply these two together, how would you round it off? How many significant figures are in your multipliers? 3 for this one, 4 for that one. So this one has to be limited to 3, doesn't it? Right. 1, 2, 3, round up. So 8.83 should be the answer. Okay, now we'll say a word about exponential versus scientific notation. Exponential notation only requires that you take the number and you store part of the number in the exponent. So if we had a number that was like this, like 123,456. If we want to make it exponential, it doesn't matter what the coefficient is, and that's what A is. A is the coefficient, and this is the exponent. This is the value of decimal notation, or decimal system. If we want to say, let's only store the decimal place, let's store those 3 in the power of 10. So that'd be 10 to the 3rd, right? Because we would ones, tens, let's see, tens, hundreds, thousands. And then what do we have left over? 1, 2, 3.4, 5, 6 times 10 to the 3rd. That is exponential notation. It doesn't matter what this is. It's just, you just have to store the size of the movement in that value, in the power of 10. Scientific notation is a special case of exponential. Scientific notation says the exponent has to be between 1 and 10. So in that case, we'd have to move it 2 more. This would be, well, this would be 5, and this would be 1.2, 3, 4, 5, 6. Okay? And this would have 1, 2, 3, 4, 5, 6 significant figures, just like this one. 1, 2, 3, 4, 5, 6 significant figures in that number. Right. Significant figures are retained in the coefficient. a lot of people, educated people, book authors, equate exponential and scientific notation, but they're not equal. Scientific is a special case. So we're going to be using scientific notation. All right. What's wrong with this picture? How many significant figures in that number? One. So there should only be one significant figure over here. Right? So that's wrong. I didn't create this slide. Disclaimer. I inherited it from the authors. And I just thought I'd make an example of them. We're making this boo-boo. That should be 3 times 10 squared. Right? Now, the understood decimal is moved over to here. But those zeros are not retained because they're not significant. Right? So 3, just the whole number 3 times 10 squared is the correct exponential notation for that number. Now this one, your example, those 3 zeros disappear. We're moving the decimal over here to the right instead of to the left. So it's 1, 2, 3. And when you move the decimal to the right, the power of 10 is negative. Right? Because you're storing up, you're making the coefficient bigger than the original number. So you've got to balance it by making this one negative, making this one smaller, to counteract that one getting bigger. So this one is correct because all of those are significant, but not those. That 0 is significant because there's a decimal there. So we keep it. 4.890 times 10 to the minus third is correct for that one. And you can go backwards if you need, right? So if you have a negative 3 here, you just move the decimal to the left. 1, 2, 3. Then you put zeros in as placeholders, but they're not significant. Oh, by the way, one of my pet peeves, let's say you make a measurement like that. That's what we call an orphan decimal, right? It has no parent. You have to have a leading 0. A lot of my students come out of public schools, and their teachers don't care about those. They say, all right, just put a decimal up there, right? But if you have anything else out here, could get confused there. This protects that decimal from anything else in your sentence messing with it. If you bracket it, that decimal with this leading 0, it's not significant, so you're not adding anything to the number, but you're protecting it. It's a placeholder. So I don't even see any orphan decimals on any of your reports. Okay. So multiplication and division in scientific notation. So let's say we have, we want to multiply. So we have 1.23 times 10 squared. We're going to multiply it by 3.47 times 10 to the 4th. Okay. So how do you do that? You do the coefficient and the power of 10 separately. Right? You've got your multiplier down here. You've got your 10. Now we need to put a value for the coefficient and a value for the power of 10. Right? So this one is simple. You just multiply that one times that one. Right? So 1.23 times 3.47 is 4.2681. I just keep everything from my calculator for now. And what is the power of 10 here?
Don't you just add it?
You add the powers of 10. Yes. There. Now you go and say, how many of these can I keep? What's legal? Well, let's see, there's 3 here and 3 here, so that means you only have 3 here. So we're going to keep those 3. That's greater than 5. So the answer is 4.27 times 10 to the 6th. Okay? Okay, let's use those same numbers. Oh, wait. I want to erase it too quick. Let's use those same numbers now, and instead of multiplying, let's divide. Okay? So just like before, you divide this one into that one. 1.23 divided by 3.47, and that's 0.35447 times 10 to the what? Now when you divide, what do you do with it?
Take a wild guess, subtract.
Yeah, you subtract this one from that one, which makes it 2 minus 4 is minus 2, right? Minus 2. Now we want to convert that to scientific notation, right? That's less than 1. Can't have that. So if we move this decimal to the right, that makes this one -3. Okay? And that would be 3.547. Now we have to do significant figures. Right? That's 3, that's 3. So we get to keep 3 here. Right? 3 of those. This is less than 5, so that means our answer is 3.54 times 10 to the minus 3. Okay? Now, what your calculator will do, that's if you do it section at a time. But your calculator will do all that for you. Right? All you have to do is know how to input exponential, exponential or scientific notation. So most of calculators have a button on there for powers of 10. I don't know what it'll be on yours. Mine's just an E. It says E, and that means exponent. Right? And then you put in the exponent behind it. If you put in a number and it needs to be negative, then there should be a change sign number, like a plus, slash, minus on mine. Yours might be a little different. You have to learn how to use it. But you can do that whole thing, and it'll spit out this number right here. Then all you have to do is correct significant figures. Okay? Now, what if you have, what if you multiply and divide several numbers together? Just string them together. Right? That happens a lot. The potential is if you do each calculation and round, and then you go to the next calculation and round, you can introduce significant rounding errors. Right? What if each one of them was rounded up each time? Your answer would be here, the real answer would be here, and your answer would be up here. Way, way off. So when you have only multiply, divide, or if you have some internal pluses and minuses, you do those first. And then once you've got those cleared up, then you do all the multiply, divide, and you do it as a string, all of them together. And you keep this, or if you do them by stages, don't round until the very end. And you go back and look at your calculations, see which one has the least significant figures, and round your final answer. You avoid rounding error that way. Then, of course, you always have to remember what's the order of operation. Well, preferably you have parentheses in there to direct your calculations, right? Because that's the first one. parentheses trump everything, right? But if you don't have parentheses, then you go to exponent, and then you go to multiply, divide, and then last priority is add, subtract. So the problem with that is, if you don't have parentheses, then you can't do the add, subtract till the end, right? So you have to avoid rounding error, you do these multiply divides, if there's a bunch of them, and you don't limit their significant figures until the end of those calculations. Then you put them together in add, subtract. I don't know who came up with that, but for scientific purposes, it's a real nightmare. Okay, so let's convert this to scientific notation with 4 significant figures. So we're given that number, and we're saying you can only keep 4 of them. So maybe it was from a calculation. It says, all right, your answer can only have 4. So we move this, there's an understood decimal here, so it's 1, 2, 3, 4, 5, 10 to the 5th. That's all over 10 to the 5th. We have to decide that 6.301 is the 4th one, 4th significant figure. 7 is bigger than 5, so it's 6.302 times 10 to the 5th. Oh, that's 6. That's not a decimal place. Should have been separated a little more, shouldn't it? So you don't mistake it for a decimal. It's a period. These are all periods. There's a decimal, decimal, no decimals. Okay, that's not right. I should have picked this one. Right? 6.302 times 10 to the 5th. Yeah. Stop me if you have questions. Are we good on time? 10:15.
You know, the orphan zeros make sense now just doing that. It makes a lot of sense if you have like a 0 before them.
Oh, yeah.
You know for sure it's a decimal.
Yeah.
Yeah.
Okay, conversion factors. Why do we need conversion factor? Well, what is a conversion factor? Conversion factor is an equivalence, or actually a ratio, that's used, that's multiplied by a number with a unit of measure to change the unit of measure to something else. Right? So if we needed to convert seconds to minutes, say we had 34 seconds. We wanted to convert it to some number of minutes. We would need a way to cancel the seconds, right? That's in the numerator, right? All numbers written plain or over 1, they're in the numerator. And this seconds, we want to cancel the seconds and leave us with minutes. So the one you're headed for is on top, and the one you're canceling is on the bottom. Cancels that one. Minute. Then we need a ratio. How many seconds in a minute? Well, there's 60 seconds. So 60 divided into 34 will give us that many minutes, whatever that happens to be. Well, I don't like taking people's word for anything. So, why do conversion factors work? Let's prove it. Not just because I said so. I heard that a lot when I was growing up. Why do I have to do this? Usually my father, because I said so. But as I got older, he's spent time explaining things to me. Just when I was little, where I got that a lot. Okay, suppose conversion factors always start with an equivalence. Something is equal to something else. So in this case, 1 inch is equal to 2.54 centimeters. So if you have an object that's an inch long it's also 2.54 centimeters long. Right? The physics didn't change. It's still that long. Same object, same length, different measurement, different unit of measure. Right? So that's why we can say 1 inch equals 2.54 centimeters. What if we divide both sides by 2.54 centimeters? Right? You can do that, can't you? In algebra, if you divide or multiply both sides by the same number, then it's a valid operation. Right? So we're going to divide by 2.54. So these two cancel each other, and what does that equal to? Well, I should have written it out there. It's equal to 1, right? Now, this ratio is equal to 1 because it's equal to this. Something divided by itself is equal to 1, right? It canceled these, and then the magnitude resolved into 1. 2.454 divided by 2.54 is 1. And the centimeters are gone, right? It's a dimensionless number equal to 1. Okay? Now, if we want to convert 100 centimeters to inches, oh, I jumped the gun. I can multiply 100 centimeters by 1. That's valid, right? But I still got 100 centimeters if I do that. So I want to substitute something that's equal to 1. Well, this is equal to 1, right? So if I put that in there, substitute it for 1, I'm still obeying the rules. If I do that, then the centimeters here cancel the centimeters there and leaves us with inches. Now that we have the units we want, we just have to resolve the numbers. 2.54 into 100 is 39.37 inches. That's 1 meter, actually. So I was off by 100. Didn't I say 39.36? 39.37. So that's why conversion factors work, because conversion factors are always equal to 1. So if you have to chain them together, say we wanted to get something else out here. Say we wanted to go to miles. You just stack another conversion factor there, multiplying by it, cancel the inches, equal to miles, or inches equal to feet, and then feet equals to miles. So you can chain conversion factors together because every one of them is equal to 1. There we go. Okay, so these equalities will produce conversion factors depending on how you need them. If this is equal to 1, then so is that, right? If that's equal to 1, you can invert it and it's still equal to 1, right? So a conversion factor that's flipped the wrong way, all you have to do is just invert it, stick it in your formula, and how do you know what to do? The one you want to cancel and the one you want to keep, right? The one you want to cancel is on the bottom because it's in the numerator over here. So you cancel that one. But if it happens to be inches over here, then you flip it this way. So inches will cancel and leave you with centimeters. Okay. There's various other conversion factors based on equivalence. 1 pound is 454 grams. We saw that earlier. 1 kilogram equals 2.2 pounds. 1 ounce equals 28.3 grams. So I used in my lab, if I wanted to know how much postage to put on a package, I'd stick it on my scale. My scale went up high enough. Now I measure the grams, and then I convert it to ounces because I knew that each ounce was so much. I usually overestimate it because I think the Postal Service says the first ounce is this much, and then the second, third, fourth, maybe less as you go up. But I didn't want to have the package coming back to me, so I paid a little extra. Okay, these are volume conversion factors, right? And this is just a reminder. We said so before, 1 milliliter is 1 cubic centimeter. So if that's the case, then this one divided by that one is 1 to start with. You don't even need to use it. If you have a unit of measure that's milliliters and you want it in cubic centimeters, just change it. It's the same, right? I'll show you an example later when we talk about density. How would we convert 4 inches to 10.2 centimeters? So it's giving you the problem in terms of what's the question? And here's the answer. The question is then, how did you get there? Right? If this is where you start and this is where you end goes on top. Right? And where you start goes on bottom. To cancel. So the one that says centimeters on top and inches on the bottom is the correct. As long as the value is right. 2.54 centimeters is 1 inch. This one's not right because of the value there. So C is your answer. We had to get this first so we know which one was on top, and then you need the correct ratio. 2.54. So which one is the bigger unit? Centimeters or inches? If you go from, if this one goes down from top to bottom, then the size of the unit goes up from top to bottom. They're inverse. So if this one decreases that way, then this one has to increase. Right? So the size of the measure, the size of the unit is bigger for inch than centimeters. Because we got smaller this way, we get bigger this way. Okay? Frowns?
Slightly.
A frown is a smile turned upside down. Okay. Now, what we've just done with these conversion factors is a form of dimensional analysis. Dimensional analysis is a fancy pair of words that just means keep track of your units. You know where you started, you know where you're going. The analysis part is how do you get there? And your conversion factors just need to be, if you've got a single conversion factor, great. If you don't know a single conversion factor, but you know relationships on the way, you can chain them together. Because if I, let's see, if I wanted to know what's the average distance of the Earth to the Sun in kilometers, right? But when I was growing up, it was all in miles. So he said 93 million miles is the distance to the Sun. But I wanted it in kilometers, right? Well, there is a conversion factor from miles to kilometers, but say I don't know it. But there's some other conversion factors I do know. Right? So I know how many feet are in a mile. Right? 5,280 feet. Now that's an exact number, so it doesn't matter whether I put a decimal there or not. Right? The only number I need to concern myself with is this one. So that says it's only got 2 significant figures. Right? So in my answer, I can only do 2. But now I've got rid of miles, and now I've got feet. Right? So I come down here and multiply it some more. I got feet here to cancel that. And I know that there are 12 inches in a foot. Right? Well, now I know the relationship between inches and centimeters. Right? So I can get rid of inches. Now I got centimeters. Now I'm in the decimal. The metric system. So now I can convert centimeters to meters, because 100 centimeters is 1 meter. Right? And now I can convert meters to kilometers. So I got 1,000 meters in 1 kilometer. Now I'm at kilometers. And I just chained my conversion factors together. I knew where I was headed, and I knew which factors I could remember. Just put them all together in a chain. Now that I've got all my units taken care of, all I have to do is say, this is in the numerator. That times that, times that, times that, times that, times that, divided by 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 that. That's my answer. Okay? I think it's maybe 160 million, something like that. But that's what chain conversion factors look like. Sometimes I use the example of if I need to drive somewhere, drive to maybe Atlanta. I got family down there. I need to know how much money to take with me so I can buy gas to get down there and have enough money to buy gas to get back. So I want to know how much money do I need. So I think, all right, what factors do I need to know how far it is, and then round trip. And then I need to know the mileage, the miles per gallon on my car. Right? How many gallons of gas do I need to go that far? And then what's the price of gas? So many dollars per gallon. Right? I can use those factors, find out how much money I need to take with me, and I pad it, I need 10% for driving around when I'm down there. Okay. So there you would use chain conversion factors to get an answer in dollars. Okay. So how are we doing on the slides? Okay. I don't want to spend a whole lot of time on this one. I think there are examples in your homework for doing these types of problems. So dimensional analysis, just you know where you're starting, you know where you want to end up. Pay attention to the units, and that will dictate what your conversion factors are going to be. That's dimensional analysis, and there are a great many problems in chemistry that can be solved with dimensional analysis. You don't even know what the chemistry is, right? You just keep track of the units. Okay. So you can review that at your leisure. Yeah, we're not going to spend time on that. You've got it all out here. Take a look at it. If you have any questions. We will still have, let's see, chapter 3 would be next Friday, right? Then the Friday after that will be a review on all those 3 chapters. And the Friday after that will be the first exam. By then, we ought to have like maybe 4 labs. So when we get to that one exam grade, then I'll combine them all and post a running average in Blackboard that you can take a look at. Just look at my grades. In fact, you ought to see in my grades now the safety lab, if you've been in there and looked. Which of the following is a feature of dimensional analysis? Units do not have to be considered. Wrong. Units must be considered because they can be multiplied, divided, and canceled. That's true. You can multiply, divide, and cancel units. Now, up to this point, we just canceled units. But if you get a calculation that has, say we have 100 joules, which is a measure of energy, and then our calculation says you have to multiply that times 20 seconds, then our answer would be 2,000 joule seconds. Or if we divide it by, it'll be joules per second. Right? We can't cancel them, so we have to keep them. So our unit of measure now becomes something like that. Okay. So that was true. Units can only be divided, wrong. Units cannot be multiplied, wrong. Is B. You can multiply and divide or cancel units of measure as well. Just treat them like numbers, except with numbers, you actually come out with an answer. But with units, if they're not identical units, you can't cancel them. You have to keep them. Now let's talk about density, because we're gonna go in the lab. Let's see. Next week. Let's do the week after. Measure density. I'm going to hand out.
Get the schedule. Okay, so we finish up graphing techniques today, laboratory techniques that get you familiar with things in the lab. And then we do a density on the 14th, on a review day.
So this is the operative calculation for density. If you know the mass of an object and how much volume it occupies, you just divide one into the other and you get the density. Okay. Now that brings up the concept of capacity versus intensity. Some books will say intensive or even intrinsic versus extensive versus or extrinsic. But they're just synonymous. These terms are a little harder to follow. I think using capacity versus intensity is a more direct approach. It's more intuitive. So if a factor is a capacity factor, it doesn't matter how much of the substance there is. But it does matter, excuse me. It does matter how much. If you have more of a substance, then the value in the unit of measure, the value of that unit will increase as you have more. Mass is an example, right? So if we have more of a substance, we're going to have more grams of the substance. That's a capacity factor. Density is an intensity factor. Mass divided by volume. This says that the density is the same for that substance no matter how much you have. Because as you increase the amount, you also increase the volume. So the density is constant for that substance at a given temperature. If it's a solid or liquid, if it's a gas, then you have to take into consideration pressure. But the density won't change. It's the same no matter where you look or how much you have for that substance. Whereas capacity factors do change. So the capacity factor in this calculation is there and there. So the mass and volume do change, but the density doesn't change. And most intensity factors are some type of ratio. Not all, most. I'm going to show you one that's not a ratio in just a few minutes. All right, so when we talk about density, usually when we identify the density of solids, the mass will be grams and the volume will be cubic centimeters. That's just grandfathered in. That's the way scientists like to talk about it. Grams per cubic centimeter. If you look at a reference manual and you look for the density of something, if it's solid, it'll be reported in grams per cubic centimeters. Right? If it's a liquid, it'll be grams per milliliter. But right, grams didn't change, and cubic centimeters is equal to a milliliter. So if you have a value, say your calculation comes out as grams per milliliter, but it's a solid, so you just change the milliliters to cubic centimeters, and you're good to go. Gases, of course, are usually grams per liter because gases are less dense. Right? They're lighter in common terminology, lighter than solids and liquids, so we need more of them. We need liters rather than milliliters to get a nice, large enough number to measure. And you can measure the density of a gas. Right? You just have to confine it. Right? And then when you put it on your balance, what do you have to do first? You have to know how much your container weighs, right? So you can subtract it from the total weight, and that gives you what's contained within. Okay. All right. So here's an example. If a mineral has this many grams and its volume is this, then all you have to do is divide them. Right? And you get a value. You get these two capacity factors give you this intensity factor, 7.57 grams per cubic centimeter. Has anybody in here had physics or physical science? Okay. Will that substance float or sink in water? What's the density of water? 1, roughly. So if it's more dense than water, it'll sink. Sink like a mineral. Sink like a rock. If it's less dense than water, it'll float. Okay? So how do steel-hulled ships float? We know steel is more dense than water, right? How do they float? Well, you can explain it 2 different ways. Either Archimedes Principle, or you can say, all right, so your ship is sitting this deep in the water, right? What is the overall density of the ship? In that case, you have to take into account everything that's in the ship and all the air that's confined to the ship. And the average density then will be less than water. It floats. Okay. Archimedes Principle is another way of approaching it. Say the mass of the ship is equal to the mass of the water that is displaced. So if it goes down that deep, the volume of the ship is so much submerged, and that displacement is so many tons of water. The ship weighs that many tons. That's why when you see reported an aircraft carrier has a displacement of 39,000 tons, that's what they mean. It actually weighs, or its mass is 39,000 tons. But the amount of water it displaces to stay afloat is 39,000 tons. Okay, what about this one? This liquid sample has a density of 0.0. They're going backwards. So that's the interesting thing about mathematical equations. We have 3 variables here: density, mass, volume. If you know 2 of them, you can solve the third one. Right? Any algebraic expression with one unknown is solvable by itself. What happens if you have 2 unknowns in that equation? You're stuck, unless you have 2 related equations in those same 2 unknowns. Right? Then you can solve them. Anybody had algebra? Yeah. Okay. So you know about solving simultaneous equations, or do you have nightmares about it?
Nightmares about it.
Okay. But in this case, we know the volume, right? 49.6 milliliters, and we know the density, right? So we got one unknown, mass. And the question is, what is the mass? So you just have to solve it for mass, right? Just move this over here, times that, and plug in those two numbers, solve for mass. Or plug in the numbers and then solve for the one that you want. Either way. That's the way this was done. So the mass is 42 grams. Now, will this one float? That liquid?
No.
It's less than 1, right? Anything less than 1 will float in water. I should have been more specific. Float in what, right? Float in water. Right? Definitely float in mercury. Right? I think that solid mineral before will float in mercury, because mercury density is over 10 or 11. So that mineral will float in mercury. So if its density is less than 1, it will float, assuming it doesn't mix with the water. Is it soluble in the water? Then you got another problem. But if, say, if the liquid is hydrophobic, that is, it hates water, like oil, it'll float. And that's what happened when the Exxon Valdez ran aground in the, let's see, what was that? It was coming from Anchorage, I think. Loaded down with crude oil from the North Slope of Alaska. And it hit a underwater obstacle. It's too close to the shore. Ripped a hole inside, and oil went everywhere. And most of it floated on top and just got scattered all over the beaches, killed a bunch of birds, fish. And from then on, the maritime authorities agreed that all oil tankers had to be double hulled. They had to have one external hull, contact with water, one internal hull separated by so many inches to actually contain the oil. So that means on the same size ship, the owners of the ship can't carry as much oil, which makes it more expensive. So they were all up in arms about that, but the governments of the world said, nah, we're not going to do this again. So they had to be double hulled. Or maybe there were some countries that didn't agree, like Liberia. That's why so many ships are flagged from Liberia, because they have such weak regulations. Anyway, that's another topic. So the definition of density. Density equals something. Volume divided by mass, oh, that's backwards. Mass divided by volume, there you go. Okay, temperature. All right, I mentioned earlier that most intensity factors are ratios, something per something. And that establishes a movement of the numerator and the denominator together. So if you get more of something, the other one changes by the same amount. So the ratio doesn't change. But temperature is an example of an intensity factor that's just a single unit. So if you have something that's 98.6 degrees Fahrenheit, human body, you, generally speaking, will have that temperature throughout. Well, we know the surface, of course, when you're trying to get rid of heat, or you don't want to get rid of heat, like you're out with no coat. But generally speaking, your internal body temperature is the same no matter where you look. That's an intensity factor, but it's only one unit of measure, degrees Fahrenheit. Well, where do these measurements come from? Right? Let's see, do I have enough time to discuss that?
We're good till 59. Okay. close. Yeah, we're good.
Okay. So where did Fahrenheit come from? It came first. 1724. And each of these is named after a person. So Fahrenheit was interested in living systems. He wanted to know how hot or cold something was. He wanted to quantify how hot or cold something was. But he was dealing with living systems, so he needed a scale that was bracketed by real world temperatures. So he said, okay, most living systems that I deal with, warm-blooded animals, are in the neighborhood of 100, or in the neighborhood of this, some temperature here. They're that hot. So this is the hot end, but he needed a cold end because 1 point does not define a line. Right? You need 2 points. Right? So he took his bottom point, his cold point, was the coldest temperature that he could get in the day. And that was ice mixed with salt, sodium chloride. And he said, that's my 0 point. And this is my 100 point. Then he can divide it equally, 1 to 100. Okay? So this is 100 degrees Fahrenheit, and this is 0 degrees Fahrenheit. Then along came Celsius, just a little bit later, when chemistry was starting to crank up, and they needed to measure things in terms of physical processes, right? Not just biological processes. So physical processes, they need something that's detached from living systems as your standard. So I said, all right, what's the most common substance on Earth and easiest to purify? Water. I said, okay, we're going to take physical phases of water and use the temperature at which those things occur as our standard. So for Celsius, the hot one, 100 degrees and 0 degrees, had to do with boiling water. You never guess what this one is. Freezing water. And then subdivide those into 100. Now, these are not equal scales, right? These occur at different places. In fact, if we try to scale them properly, this is 32. Right? Everybody knows freezing water. And 0 is way down here. And 100, actually boiling, is 212. Right? So 100 is in here somewhere. Now, if they're scaled properly, the only difference between the two now is the size of that unit. How big is that division? But Celsius wanted something that could be reproduced anywhere. So most competent scientists of the day could obtain pure water. They knew how to distill it. That was the most common way to acquire pure water. And then you just measure the freezing point, or you get ice and liquid water together at the same time, stabilized. As long as they're both there, then you stick your thermometer in, that's your 0 point. Or if you have water boiling and you submerge your thermometer in the boiling water, as long as you have both vapor and hot water there together, then the water is going to be 100 degrees. And that way you can calibrate your thermometers. Well, along comes Lord Kelvin. His curiosity had to do with gases. So he noticed, and based upon a Frenchman by the name of Charles, his last name is Charles. Charles' work, Charles noticed that with temperature on this scale and volume on this scale, as the temperature increased, the volume increased of a gas. So he noticed that it was linear. So if the temperature doubled, the volume doubled. Okay, you could draw a straight line. But nobody knew what happened on the either end. Okay. Well, Kelvin said, just for giggles, what if we extend this line, right, and keep dropping the temperature until we get to 0 volume, right, where the gas has no volume. Okay. At that point, he said, all right, if there's no volume left, we can't shrink the gas any further. That's my 0 point. Whatever that temperature is, that's 0 K. Not 0 degrees K, just 0 K. Okay? So that's his 0 K. What's that relationship to degree C? Well, as it turns out, degree C then is minus 273. So 0 K and 273 are the same temperature. Now, can you really get a gas to disappear? No. At some point along here, that gas will turn to a liquid. You know, and some of them will even turn to a solid before they get to that point. But it's valuable for dealing with gases and other temperature calculations in chemistry because there's no negative K. They're all positive numbers. So you don't have to deal with signs. Like, all K temperatures are positive. Okay, so that's what Kelvin said. And then he said, so anytime you have degree C, all you have to do is add 273 to it, and you got K. Okay. Because the size, the units are the same size for each. So 1 degree K is exactly equal in size to 1 K unit is equal to 1 degree C unit. Okay? Now, there's another one that does a similar thing for Fahrenheit, but nobody uses it. It's called the Rankine. So it'd be so many R's, but nobody uses it. Okay. Maybe Rankine thought he was going to make a name for himself, and people just ignored him. Okay. So we'll talk about that a little more when we get to our chapter on gases. And that's one of the more enjoyable experiments when we do Boyle's law, pressure and volume. We don't do Charles' law. It's a little bit too complicated. I don't have the equipment for it. It was really easy to build stuff for Boyle's law. So that's what we'll do eventually. Okay, so the point here is that the physics is the same. Wherever you're at here, the only difference is what unit of measure and magnitude are you using to express that physical condition, right? The amount of heat is the same. Right? It's just which system are you using. So that means that if we can develop a formula that converts, well, I showed you the one to convert from Celsius to Kelvin, right? And you can solve for Kelvin too. I mean, you can go back the other direction, right? You got two unknowns. So if you have a value for one of them, you can solve for the other one. So if you know one formula, you got both of them. And then the trick is converting Celsius and Fahrenheit, right? So we need two relationships there. Not only does the 0 point shift here, but the size, the unit of measure shifts, right? So in order to convert Celsius to Fahrenheit, you need a little more complicated formula. you know Celsius, you can convert to Fahrenheit using this sign. This adjusts the 0 point, 32 degrees difference, like 0 degrees Celsius is 32 Fahrenheit. And this compensates for the size of the measure. Because the Fahrenheit is a smaller number, a smaller unit than centigrade. Is that right? Yeah, that's right. F equals 9/5. Some books will say 1.8, which is the same thing. 9/5 is 1.8. And if you know this formula, and that's the one I memorized, then if you know that one, you just use it. If you know this one, then you just rearrange it and solve for that one. Okay, so there's Celsius and Kelvin, and this is Celsius and Fahrenheit. Now, if you want to know how that formula is derived, there's a real good explanation right here, that location. You know, so we don't have to take up class time to just, if you really want to know the mathematical derivation, that's a good explanation. Then there's one other question that I was always curious about was, well, if the degrees are different, and based on that slope, if you draw a centigrade slope and a Fahrenheit slope of a line, they're going to intersect somewhere. So at some point, the temperatures, the units, not the units, the number or the magnitude is going to be equal for both of them. So at some point on their scale, they cross, and at that temperature, the temperature in Celsius is equal to the magnitude of the temperature in Fahrenheit. So I want to know what that is. So you take this relationship, see, we've flipped it around to where it's Celsius on this side and Fahrenheit here. And if you let X equal both of them, right? Because we want to know where they're equal, so that means if this is X, that one has to be X. So if you say X here, and then solve for X, X is equal to minus 40. So if you plug those numbers in, minus 40 here, minus 40 there, it'll resolve to the same value. They're equal. So at minus 40 degrees Fahrenheit, it's also minus 40 degrees Celsius. Now, has it ever been minus 40 around here? No. I've lived here since 1989. And one time, the temperature dropped to minus 15 degrees in Beckley. Right? It was the strangest thing I'd ever seen. The sky was just a brilliant black, bright blue. And there were snow crystals falling out of a clear blue sky. It was so cold that the moisture in the air couldn't stay dissolved in the air. It solidified. It just, ice crystals fell. So it's wild. I also know what minus 40 degrees feels like. I used to work for a company in my youth. It was a hotel and restaurant food supply. Right? So we had dried goods, supplied to our restaurants and other places that needed it. And we also had a cooler where we conducted our mostly meat handling, right? You need fresh beef. We had customers that wanted freshly ground beef. So we'd bring in whole carcasses, and we had butchers back there cut it up, throw it in the grinder, or make steaks out of it, whatever the customer needed. That was at one temperature, which was above freezing. It was like maybe 35 degrees, between 35 and 40 degrees Fahrenheit, above freezing. And then we had a freezer for long-term storage, and it would be about 20, between 10 and 20 degrees Fahrenheit. And then we had one that we used when we made stuff like maybe hamburger patties. You want to freeze them really fast, because the faster you freeze them, the fresher they are when you thaw them out. That's because biological material is made of cells, right? So the slower you freeze aqueous solutions, the bigger the crystals, right? So if you freeze it slow, then the crystals get big enough to poke through the walls of the cells, right? So when you thaw it out, you just got mush. You don't have any structure. But if you freeze it fast, the size of the crystals are so small that they don't damage the cells, right? So we want to freeze these hamburger patties really fast. So they have this one location in the facility called the blast freezer, and it was maintained at minus 40 degrees Fahrenheit. It was really cold. You couldn't stay in there more than 10 or 15 minutes. But once a month, we had to do inventory on all our products. And since I was low man on the totem pole, I always got to do the blast freezer. So I go in for 10 or 15 minutes with my clipboard and my big insulated parka, gloves. And I used a really big pen because I had gloves on, so I could. And I'd stay in there for a little while, and then I'd come out. It opened into the cooler area. It felt like summer out there. But it was minus 40 degrees, so I know what 40 degrees feels like. And your breath would just fog. Okay. Temperature reading significant figures. Let's see. Read a thermometer to estimate the temperature to the closest degree. Uncertainty then would be in the ones place. So in this case, that's two significant figures, right? Either one. For this one, there would be three significant figures. Right? If you're going up to 100 or greater. The thermometers are accurate to 1 degree in this case. They make thermometers that have tenths of a degree divisions, but just don't let students use them because they cost too much. And then, of course, now we have electronic thermometers. Right? They use a thermocouple and a wire that goes to a device, and it interprets the change in resistance in that thermocouple with temperature and tells you to tenths or even hundreds of degrees. Maybe I can bring one when we do temperature measurements. Okay, convert C to K. Right, so if we want to know what K is and we know what C is, then it's what? C plus 273 makes K. Okay, so these are ending questions that you can deal with on your own because we're out of time. We need to get to the lab. Anybody know what trazodone is? I think it's some kind of an antidepressant. But my son had trouble years ago with oppositional defiance. He was going through that phase of teenage years when you experience hormone toxicity. He became very violent. So we sent him off to Chicago for a year to a residential treatment facility. And they tried various drugs to help him calm. And one of them was trazodone. It worked for a little bit, calmed him down, but it didn't last very long. It just turned him into a red-eyed zombie. So they quit doing that. Okay. So, let's see. You want to take a short break before we get into this? We can do it in here because it's just drawing. It's just your graphics, right? Then we don't have to transfer everything.
I left my calculator out in my vehicle. Should I run and get that real quick?
Yeah, sure. We can all take a bathroom break while he's doing that.
all the way home.
Let's see, I want to pause